I think I'm live. I think I'm live. I think we're live. I think I have the volume of my computer turned down so low that I wasn't even sure anything was happening. But welcome to Tuesday and the O-Scope Wizard. I'm Gabe, the O-Scope Wizard, and it is Band Shirt Tuesday. Hopefully everyone is following along. Today, the band whose shirt I am wearing, repping, is the Cloud Cult. Can you even see that? Super dark. There we go. Cloud Cult. I don't know if anybody's familiar with that, but this band tours with painters. So I went to see a show, and during the show, two painters will paint it's not a portrait. It is just a canvas. They'll paint a canvas, one of each painter, and then at the end of the show, they will auction off those paintings and then use the money for charity and the band, which is an awesome idea. It's super duper cool. We have struggled over and over with potentiometers and what I was calling angry cicadas, which is a combination of noise caused by our power supplies, our audio output was causing some noise, our overall 24-volt power supply was causing noise, our DC to DC regulators, our Raspberry Pi, all of this was causing noise. But also, unbeknownst to me, the potentiometers themselves were causing a little bit of noise and were not doing an awesome job, and they should have been doing a much better job. So, if I turn this off and we look, I have some potentiometers lined up right here. Let's get a little bit more light on it so we can see a little bit better. But I have the original potentiometer, which is the analog potentiometer, the passive potentiometer, not digital at all. It just uses a screwdriver to go from counterclockwise to clockwise. Then I have our first digital potentiometer. It's this itty bitty chip. It's still in the tape reel here. And I soldered it to a board, and we're going to look at this. This is the MCP42100. I have the MCP42100 and the 42010, which is a 100K version and a 10K version. And then I have a third digital potentiometer, because if you can buy two, why not buy three? Well, we just have so many digital potentiometers, and we're going to compare them all today on the show. And I want to figure out which one is actually going to work best for an audio application. Also, I'm going to take you kind of through my process of how I chose these so that you can understand how to use Google. I don't know if this is a problem for you, but when I start a project and I don't know what I'm doing, but I think I know what I want, I go to Google. So this is what I did. I think I did dual digital potentiometer. And I clicked go. And this, look, number 2 right here. This is the one I got. The one from DF Robot. It is the MCP. It is this chip right here, the MCP42100. So that is what I Googled, that is what I found, that's what I bought. I thought I was great. I thought I was golden. This chip has turned out to not be great for audio applications. So then I pondered, was it because I had purchased the 100K version of this potentiometer? So I purchased the 10K version of this potentiometer, and that is this little chip right here. So this is the 10K version of the potentiometer, and we're going to try that out today. But the way our ears hear noise, volume increases logarithmically, so you want your audio potentiometer to be logarithmic. So then I was like, this is not logarithmic, this is a linear potentiometer. So I did a little bit more Googling, and I think I found a logarithmic potentiometer, which is right here, because it's the second one right here. So I bought that, the DS1841 logarithmic resistor, and I thought, hey, we'll try that. So we have this wired up as well today. But one of the things that you learn, Google is going to show you what you ask it. That's the way Google works. Eventually, you will figure out what you want to Google. So now I have Googled digital audio potentiometer, which is what I should have Googled to begin with. And it will take you to this guy, the DS1882. So, when all is said and done in our project, I will have purchased 4 different digital potentiometers, wired them up, and tested them all. And today, we're going to test the 3 that I have in my hands right now. So, I don't have this guy yet because it was back ordered. I guess once we started this project, everybody wanted a digital potentiometer to add to their Sonos-Style DIY audio amplifier based on a Raspberry Pi. So that means I have to wait to get my little digital potentiometer. So we have this one. It is a logarithmic potentiometer, but it does have something that I did not notice until it arrived, which is a 3.6K fixed resistor. And so that isn't awesome news for an audio application that controls volume. That means that your volume can never go to 0. And this guy has been doing some weird stuff to the signal so that my output doesn't sound good, which is also not awesome for an audio application. Let's get into it a little bit. So I have hooked up over the weekend. I have these 3 potentiometers. We're going to measure we're just going to measure resistances today, and then we're going to feed in a signal, and we're going to see what it looks like. If I pull the top off of my amplifier, we can see a lot of, we're back to a mess. We're back to a mess. On the back of the amplifier, I have my cement resistor. This was a little bit of fun. I was over the weekend doing some testing, and it gets really loud when you're just sending a tone into a speaker. It's just like, ooh. It is annoying and loud, and the children are going to come and investigate why is Dad making this annoying noise. So I hooked up my power resistors, my handy dandy cement resistors, which I'm really digging those cement resistors. Get yourself some cement resistors. And then I noticed a smell. A distinct smell of burning wood, and I picked up my resistor and I realized, oh my gosh, can you guys see this? I charred my desk. That power resistor, man, it was power resisting and charring my desk, which is intense. That is an intense smell. It was unintentional and pretty incredible. So we'll try not to char my desk anymore. I think my desk is well, good, and charred. And we're going to actually try to make some measurements. So if I can point my camera correctly, there we go. I have a couple resistors wired up. I have one just sitting out in space. This is my 10K MCP42100. Here I have my logarithmic digital potentiometer. It's the DS1841. If you want to follow along at home, hopefully you do since you're watching the show. And then I have the original digital potentiometer that I purchased, the dual channel, because it was dual channel. That I thought that was going to be important. This is the MCP42100 100K dual channel potentiometer. And of course, I have my trusty multimeter back there that's going to measure the resistances. And I have my original analog, just passive potentiometer, like original potentiometer that I pulled off the board. So let's measure some resistances. I am curious about the maximum resistance that I can get and the minimum. So here's my circuit diagram. The audio comes in to point A of my potentiometer. The audio goes out, the wiper in general, and then there is a second resistor from the wiper to ground. That is my circuit. And I want to know what happens when I send my potentiometer all the way clockwise, or all the way counterclockwise, and then all the way clockwise. So that means the wiper goes all the way up here and then all the way down here. So what are these two resistors at those extreme points? And how does it affect my audio signal? Let's start real simple with the old analog potentiometer. And I have, to make all of this super easy, the man, the myth, the legend is on the chat, who turned me on to J-clips that make hookups so much easier. So I have popped off the ends of these wires and added J-clips so that I can much more easily connect my multimeter to my different pins. So I'm going to connect to the A pin of this potentiometer, and I'm going to connect to the wiper of this potentiometer, and I am going to adjust the wiper position to the two extremes. So I'll go fully to the left. So it looks like fully to the left. My resistance is, you guys see that? 2.18 kilo ohms is what it's looking like. Let's make sure I got a good connection here. And now let's go the other direction all the way. Is that the whole direction? I think 3.2 ohms. 3.2, that's pretty low. That is pretty low. Oh, here we go. I didn't have it the other way. So fully to the left, 9 kilo ohms. That's good because this is set to be a 10 kilo ohm potentiometer. And then all the way to the right, all the way clockwise, 3 ohms. 3 ohms. That's low ohms. So that is how, that's how the original component worked. It swung. This resistor right here goes from 3 ohms all the way up to 9 kilo ohms. And this resistor goes from 9 kilo ohms all the way down to 3 ohms. So you essentially have a short to ground here while you have a 10K resistor on this side. Do any of my digital potentiometers match that? So we were measuring from point A to point wiper. So let's do that on all of my digital potentiometers. I have changed colors of my volume knob. One of the things I did, let's see if I can, actually let's crank up my software that actually communicates to all of this, because it is an embedded system, so it requires some software to go. These are digital potentiometers. You have to tell them what you want them to do. They don't operate passively, which is a blessing and a curse. I can tell them what to do even when I'm not operating them, but if I don't tell them what to do, they don't do anything. They are like children. Is that a dad joke? That might be a... I'm going to count that as a dad joke. Everybody laugh. So let's crank up my interface. I have decided that I'm going to do some coding off camera because watching people code, maybe not the most exciting, but I will release the code so that if you want to try it yourself, hey, you can download it and give it a go. So I've cranked it up. I call it now the Sonos Amp Interface. And it is running right now. If I go back, I can see I'm controlling lights here. I've made them pink because I like the color pink. But this, when all the lights are off, I am fully counterclockwise. So my resistance between point A and point wiper should be at its maximum. So let's measure the resistors. I have all the resistors wired up, and I need to make sure that I'm measuring the right parts, but I should be able to. So we will start with our original. So we'll start with our 100K dual channel potentiometer. Use my handy dandy J-clips to do it. We'll see if I need to add. I kind of have a cheat right here to make it a little bit easier. since I'm using 100 mil headers, I can clip onto these guys and get onto those header pins. So let me make sure that I actually probe the right component. So according to my very sophisticated wiring diagram, I need to probe the pin to the farthest left and the one right next to it. So PA0 and PW0. Let's probe some potentiometers. I have done so much potentiometer research for digital potentiometers that I had never really even considered any of this before. This is all pretty new to me. So I've learned a lot. That is faux show. I'm not sure I'm getting a great connection there. Let me make sure. Oh no, it's working. Here we go. Here we go. Here we go. So the resistance with the original potentiometer here, when you are at the maximum amount of potential between point A and your wiper pin, for the MCP42100, it is 413 kilo ohms. You know what? We should probably document that. We should document that. We have the technology to actually do that. So let's just write it right here. So we will say MCP42100. We will call this max, or actually we should call this min, meaning min volume. Minimum volume, 413 kilo ohms. Now, since we are plugged into it, let's do max. So what is the resistance when the volume is at maximum? That looks super weird, but that's okay. It'll get a little bit better. In fact, we could probably make it get better by just... Does that make it get better? No. Let's make it get better. We will also do this for the MCP42100, and then we will do it for the DS1841. And of course, we did it for the passive component. We already have that value, so the min was 9 kilo ohms, and the max was 3 ohms, just like 3, which is like a super low. So the min volume, 9 kilo ohms, max volume, 3 ohms. Oh, and we can't see 3 ohms, so let's just measurements. Let's just put something down there so that we can see all of the values. There we go, all of the values. Solid, solid. Our bookkeeping probably could use some work. Wow, we're still working on it. Okay, we're gonna make this max volume. So if I zoom out here, we should be able to see the lights light up, indicating that I am changing the volume. Solid, you can see the resistance dropping up here. So what does it get to when we go to max volume? Is it really only getting down to 63 kilo ohms right here? This is one of the things that I was really struggling with. Let me take out my extender wires and just push my J-clips on. One of the beauties of J-clips is that they do fit onto headers, but sometimes they can be a little bit loose. Which is one of the worries I had with making a solid connection. But here we go. Here we go. No, it's going from 430 kilo ohms to 64 kilo ohms. And this, I will admit, when I saw it getting stuck at 64 kilo ohms here, it made me wonder if that particular potentiometer had a problem. So 64 kilo ohms. That ain't good. We want this number, the max number, when it should be at max volume, to be very low. Kind of like tennis, when it is max volume, or you're going for the lowest value at max. So now let's measure its brother, the MCP42010, which is the 10K version of this dual potentiometer. I have it. This is the one that's kind of just hanging out in space over here. We're going to make these measurements. So let's go all the way back down using the same SPI bus to communicate to both this chip and this chip, since they use the same commands. So I have them kind of wired together. That is one of the beauties of digital logic. If you get it working, you can change components as long as they have the same pinout and use the same commands, and get different values. So this should go, I'm guessing, somewhere between, so when it goes off, it should still be about 430 kilo ohms, and when it's all the way on, I'm hoping it is lower than 64 kilo ohms. But I need to check the pinout really quickly, because I can't remember exactly how this thing is wired. So PA0 is the bottom right, and so pin 8 and pin 9. So if I go back, oh my gosh, woo, we're gonna go a little long today, guys. We're gonna go a little long. I'm not even gonna hit 5 minutes remaining, because we gotta make these measurements. We gotta make these measurements. It's a big deal. I wanna make sure that we measure everything. So pin 8 right here, pin 8. Ah! Goodness gracious alive, can I make a connection? Just because the J-clip's supposed to work, it's only as good, the operator error is high. Operator error is high here. We're getting there. Oh goodness. Let's make sure we're getting a connection. Oh, I might be messing stuff up by holding it. There it is. I can't short wires. That's no bueno. All right, so we are at minimum volume here. Can we see? Yep, we can see both the lights for my volume, and I can see the screen of my digital multimeter. So, okay, minimum volume right here is measuring 384 kilo ohms. So let's record that. If I can type. So minimum volume 384, so we'll type min 384K. And then if I turn it up to max volume, min 384K. Max, what is max? So let's turn all the lights on. Ooh, you can see that resistance dropping, It's only dropping down to about 6K, I don't know, 6K. It's just doing some weird stuff. It's doing some weird stuff, and I can't tell if it is because of my coding or what, but I'll tell you what, this resistor does weird stuff to the sound. But look, proportionally, those are the same. So I think I might be writing an incorrect command right now. That is a chance. I might only be writing half as much to this resistor as I should. Could be having a coding problem, guys. Ultimately, it won't matter that much, because what I have learned from this exercise is that the MCP42100 series of digital potentiometers is just not good at audio. It just doesn't sound good. Like, your ear holes can tell that something is wrong with the audio. So ultimately, I wanted to make these measurements, but I cannot convey how bad it sounds through this video medium with this tiny microphone, because I'm streaming, so you're like, man, I don't know, it doesn't sound that bad to me. But trust me, it sounds bad. Now let's measure our last one. So this is our logarithmic audio potentiometer, and it has a problem of its own. So let me connect up to point A, and I have volume all the way down. Good. Point A and wiper. So the volume's all the way off. So before, this was super high, right? This was like 3. Oh, the chat asks, can I describe the audio signal that you're passing through the digital pot? Yes, I was passing music through an AirPlay device. Oh, I just hit my mic. Sorry about that. I was passing music through an AirPlay source from my iPhone to my Raspberry Pi. My Raspberry Pi sends the audio signal over to the DAC, the digital analog converter, with I2S audio signaling. And then the DAC sends that audio signal, the actual audio signal, to my amplifier. And I have been using music. I have done just tones from my iPhone with the tone generator. Today, we probably won't be able to get to it because I'm running short on time, is I have the oscilloscope's signal generator just running directly through my potentiometer into my audio amplifier. So we have a very clean source, maybe even more clean than music. The problem with music is you can hear it instantly with your ears, but it's very hard to measure because it's a very broad spectrum. So it's much easier if you can narrow down your audio signal to a single tone or a single note or a single frequency and run that. And then you can sweep that frequency around, but you can look at one frequency at the time, and it makes it a little bit easier to quantify the problems that I'm seeing. Let's see. The question is it sourced from an op amp that I'm trying to attenuate before it gets into your power amp? It is straight, so I am essentially, the audio signal comes straight from my digital to analog converter chip. It would be as if I was running it straight out of the headphone jack of my phone into the audio amplifier. And before, the potentiometers were analog, and they would just basically adjust that voltage to make the voltage bigger or littler. The digital potentiometers are trying to do the same thing, but what I'm finding out is that the original MCP42100 series of family that I got is really catered to DC voltages, so it does a great job of acting as a DC voltage divider, but it has a real problem with a full spectrum signal like an audio signal. It just can't react fast enough or has all kinds of feedback. It has a breakdown voltage that makes it sound bad. So that is why I was led to this logarithmic, this DS, what did I say, DS1841. It's like the first thing that you get when you Google digital potentiometer from Adafruit, so I bought it. But one of the things that happens is I have the volume all the way down, and the other guys had super high resistances, and this guy peaks out right here at 3,500 ohms, so 3.5 kilo ohms, which is not nearly as big. So one of the questions has, have I tried using my digital pot to adjust the gain of an op amp? No. That is a good idea. Is it beyond my capabilities? That would be a cleaner solution. The op amp would be able to act as a buffer between my digital to analog converter and my actual audio amplifier. And it would add one more layer of awesome. I hadn't even thought of that, because what I'm also struggling with on the back end is as my power goes more and more places on this pretty big board, I'm getting noise problems. So I've tried to minimize the actual other components that I have in this system, because I have a relay to switch between external and internal inputs. The op amp idea isn't bad, though. I'll think on that. I mean, I also have coming in the mail this potentiometer that is specifically made for audio signals, to run an audio signal in from an audio preamp directly out to your amplifier, which I probably should have purchased in the first place. But as I was saying, when you Google something, you don't even know where to start. You're just Googling randomly, and eventually you kind of find the keywords. But maybe I'll also see if I can track down a little op amp, an op amp circuit for the input. That might be kind of neat. Back to my measurements really quickly. So, minimum volume here, 3.5 kilo ohms, meaning that my volume will never turn off because it's just not enough resistance. Okay, so min 3.5K. And then let's do max volume. What does max volume look like? So min is 3.5K. What does max look like? If I turn my volume knob all the way up, get the pink lights all the way on. Uh-oh, 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 uh-oh. I might have shorted something. My code's not working anymore. Hold on. Let's restart my amplifier here. What have I done? Oh no, guys. Oh no. Oh, there we go. There we go. Waking up, I think. Have I made a wire short out somewhere? Holy moly. It's just really slow, I think. Okay. I'm not getting that super hyper responsiveness that I expect. Well, I've done something to my Raspberry Pi, and it is not happy. Oh my goodness, we might have to stop there. This episode has been a lot of pontificating. It was supposed to just be some voltage measuring, but it's mostly pontificating, I'm afraid. Which is ironic. Yeah, I don't know what I have done. Somehow my rotary encoder has come unglued and now is not responding to my... Look at that. That is a bummer. Oh well. Oh well. That happens, guys. That happens. Sometimes a wire comes loose, and I'm not sure which wire came loose. But ultimately, what I have learned are that the digital potentiometers that I chose were poor choices. They just were not good replacements for an audio system. So I have ordered a digital potentiometer that I believe will work well, a DS1882. I'm going to have that in my system for the next episode. And I'm going to take the suggestion in chat to maybe look at an op-amp circuit to control the volume. That might be another way to effectively control the volume, do some pre-filtering, which I can also do digitally with the Raspberry Pi, but I could do analog, and I could have more fantastic knobs and buttons on the front of the oscilloscope, or in front of the DIY Sonos-Style Raspberry Pi based amplifier. Thank you so much for joining. I'm going to hang out in the chat, and I will see you guys not on Thursday, not on Baby Friday, but on next week on Tuesday. Don't forget Band Shirt Tuesday, so wear your favorite band shirt. Let me know what it is in the chat, and let me know what you guys think I should add to the system. The op-amp suggestion is great, so let's see if I can figure out how to easily add kind of a tiny little op-amp circuit with a potentiometer. I appreciate it. I don't know all the nerds in the world, so please share this with a nerd in your life. And I will see you guys later. Take it easy. Have a wonderful day. Bye.